modeling. As you probably know, most of the software that reaches most users today comes in the form of stripped binaries, which means that we don't have any source code or any debug symbols attached to that code. And one thing we'd like to know about this new software is whether or not it introduces any vulnerabilities to our system. And one of the ways to answer that question is using reverse engineering. And reverse engineering is the problem of taking a program in binary form and understanding what it does, and more importantly, the specifics of how it does it. And usually the first step in doing that is to statically understand the control flow of the program. So if I have some binary containing some functions, I'd like to be able to determine the edges between these functions. Okay? If we focus on a single edge, even determining that single edge can prove to be very difficult if that edge is the result of a call to a virtual function. Okay? The reason is that the target for such a call would be dynamically computed instead of statically determined, and therefore we have no easy way of statically knowing the target. And in such cases, we're going to have many possible targets that the reverse engineer needs to consider before we can understand what the program is doing. We want to assist the reverse engineer by helping him focus his efforts on those targets that are going to be more likely. Okay? And the way we do it is by producing a ranking of each of the possible targets for each of the virtual calls. To do that, we first need to remember that each virtual call is usually applied to an object, and the target of the call is determined by the runtime type of that object. So instead of directly producing a ranking of targets, we can first produce a ranking of most likely types per object and use that to deduce the ranking of targets. So if we have the same situation as before, and let's say that O is the object used in that virtual call, we have two cases we have to consider. In the first one, in the lucky case, we can statically determine the type of the object, for example, if it was recently initialized. And that object, we're going to refer to it as a labeled object, which means that it has a known type, and therefore only a single possible target. Okay? But in many other cases, that's not the case, and we're not so lucky. And the object can be of one of many possible types. And in that case, as I showed you before, there are many possible targets. And for these cases, which we're going to focus on, we're going to rank the types and deduce from that the ranking of targets. So we base our approach for doing this on the observation that different types are usually used differently. And we can use these different usages to distinguish between the types. And we rely on a combination of program analysis that we're going to use to extract usage profiles describing how each object is used, and machine learning that will reason about these profiles, and we're going to use it to predict the types of the unlabeled objects. We split our approach into 3 phases. In the first one, we're going to do the extraction of usage profiles in a form that we call trace sets, and I'll show you what it means in a couple of slides. Then in the second stage, we're going to take the profiles for the labeled objects and use that to train models for each of the types. And in the third and last stage, we'll take the trained models, the profiles for unlabeled objects, and predict the types of the objects, and from that, deduce our target ranking. So for the rest of my talk, I'm going to elaborate on each of these steps, focusing on the extraction, training, and querying of the model. But first, let me remind you a bit about virtual calls. So if we look at the assembly code on the right side of the slide, the highlighted instruction call edx, that's a virtual function call. And the target of that call is computed using the above 2 instructions. And we can use these instructions to determine that the target is represented by the expression dereference edx. Okay, so let's understand what this expression actually means. So initially, EAX pointed to some address in memory. That address holds a type instance, an object. And in the green instruction, the first instruction, we dereference this address and return the first field of the object. So now ECX points to the first field, which is the address of a table containing all the virtual functions of the object. Then in the second instruction, we dereference that table, returning the first field of that. And now EDX points to the first virtual function of the object, and that's going to be the target that we're jumping to, that we're going to call. But more importantly, what we learn from doing this is that the object object used in this virtual call is the object pointed to by EAX. Okay, so we're going to use EAX as an expression to represent that object. And what we want to do is now to use this object and extract a usage profile for it. So like I said, these usage profiles are a relatively high-level representation of how the object is used. And more specifically, we're talking about intra-procedural sequences of actions applied to an object. And these actions can be field accesses, calls to virtual functions, and many others. And if we return to our previous example, first we can see that besides EAX that we saw before, there's also a second object pointer used in this code, that is ECX, that is used in the first block and the last block. And we can track the actions applied to each of these object pointers, and we get this set of actions. And just to make sure everyone understands what it means, so if we look at the first one, R ECX 0 means a read of a field of the object pointed to by ECX at offset 0. Okay? Similarly, W is for write, and C is a call to a virtual function. And using these actions and the control flow of the program, we can get the usage profiles for each of the objects, and we get what we see on the slide. And the interesting one to focus on in this case is the one for the object pointed to by EAX. Now, because EAX is used in a loop, what we get is a sequence that is potentially unbounded. Okay? So to bound the length of such sequences, we're going to split them into what we call tracelets, which are essentially subsequences of a fixed length. And whenever we encounter a loop, we can just exhaustively repeat that loop until we've extracted all possible tracelets from the loop. So if we take the unbounded sequence we saw before and split it to tracelets of length 5, we get the 5 tracelets you see at the bottom, and you can see for yourself that there aren't any other tracelets that we may have missed. To do all of this, first of all, we want to do it statically, and we do it using symbolic execution, where essentially we're tracking the actions applied to symbolic objects instead of a concrete one. And at the end, what we eventually get is that each object is represented by a set of tracelets, and instead of just one usage profiles, we get a set for each object. Okay, now at that point, we've actually finished the first phase of our approach, and we have our tracelets for each of the objects in the code. And now we can go ahead to the second stage, train our models, and use them to predict the types of unlabeled objects. So first, we need to understand what kind of models we're looking at. So the models we're focusing on in this work are statistical language models, where essentially if I have some language L using some alphabet, I can say that M subscript L is a model trained for that language. And whenever I'm given a sentence using letters from the same alphabet, that model can compute the probability that the sentence originated from the language. Okay, so if, for example, I have a model representing the English language, I can probably say that the sentence I am giving this talk is more likely than the sentence this talk giving I am. Now, it's important to remember, though, that this result is only correct for that specific model. And if I had a different model, I might get a different result. So if, for example, I had a model representing the way Yoda speaks, it's possible the second language would be more likely than the first. Okay? Now, there are still many kinds of statistical language models, so let's narrow it down a bit more. And we're looking at models that are also variable order Markov models, specifically n-gram models, which means that the sentences are of length n. So if I'm taking the same sentence from the previous slide, I am giving this talk, and splitting it to n-grams of 2 words, I would get the 4 shorter sentences on the right side of the arrow. And these n-gram models are usually fixed order models. By order, in case anyone is confused, order means the length of the sentence. So n-grams are usually fixed order models. And we're actually using a variant of them, a variable order variant of n-gram models. And the reason we do that is because it allows us to choose the appropriate order based on the data that we get. So if we have enough data, we can use a higher order model with longer sentences. And when needed, we can revert back to a lower order model and use that instead. So in our setting, the alphabet that we're using is actually the set of all unique single actions that we found in our tracelets. And the sentences are the tracelets themselves. And now that we understand what kind of model we're looking at, we can go ahead and train it. And I'm going to describe the way we train a model using the prediction by partial match algorithm, which is what we used in our implementation. This algorithm originally was proposed for compression, but it's also very useful for prediction. And whenever we're given a set of sentences to train the model, at a set of tracelets, what we do is we pass each tracelet to the model. The model can then pass this tracelet into n-grams. And then from these n-grams, it builds a probability tree describing the language. Okay? And now, as users, we can use this tree to query the probability of different sentences. So if, for example, I want to know the probability of the sentence A1, A1, A2, I can just follow the path along this sentence, multiply the probabilities on it, and compute that the probability of A1, A1, A2 is 0.2 or 20%. Okay? So we do this for all the types that we found in our binary. And now that we have a trained model for each of the types, we can use that to predict the types of unlabeled objects. So to do that, what we're going to do is we're going to compute a probability or a likelihood score for each object and type pair. And then we're going to rank the types for each object based on that probability. Okay, so to do that, we first need to remember that the model can already compute the probability of a single tracelet. Okay, so we define the probability of an object as the product of probabilities of all of the object's tracelets. Okay, it's pretty straightforward. As a side note, an alternative could be to train a model for each object and measure some distance between them. But in this work, we've opted to go with the product probability instead. At this stage, we've actually finished our prediction, and we have a ranking of types for each object. And now, using this ranking and the knowledge of which object is used in each virtual call, we can deduce the ranking of targets that we needed for our calls. Yeah. Well, in the time that I have left, I want to discuss our evaluation a bit. So we've evaluated this approach on 20 benchmarks, which we compiled, optimized, and stripped. And a nice observation in this context is that while optimizations are usually considered a bad thing for program analysis, in our setting, they're actually quite useful because the inlining performed as part of the optimization would result in longer sequences, which are more descriptive and therefore more useful in distinguishing between the different types. So we got our 20 benchmarks, and we manually reverse engineered each of the benchmarks and compared it to the source code that we had to get our ground truth. And then, after we get the results from our technique, we compare them to our ground truth. We can evaluate our results based on the rank assigned to the target that we expected to get according to our ground truth. Now, I want to give you some intuition for why we're evaluating it like that. If we recall the scenario we had at the start of the talk, the reverse engineer had a binary he needed to analyze. there are many possible targets, and we gave him a ranking. But still, the reverse engineer can't consider all the targets, so he needs to decide how many targets he's going to look at for each call. And let's say he decided he only wants to look at 2, so we can eliminate the other less likely ones and have him focus on the 2 most likely targets. And the higher the rank of the expected target, the less functions the reverse engineer can look at, can consider for each virtual call. So that's a bit of intuition to why we want the rank to be as high as possible. And I want to look at one specific benchmark that we had. This is a benchmark called smoothing EXE. The graph I'm showing you here isn't the actual graph. You'll see the actual graph in a second. This is just easier to explain that way. And the x-axis, that is the number of targets, the number of functions the reverse engineer is going to analyze, is going to consider for each virtual call. And the y-axis, that's the percentage of virtual calls for which the expected target was ranked at most x. Okay? So in this case, in this benchmark, the maximum value for x is 71. The reason is that there were 71 types in this benchmark, so at most 71 targets for each call. And we can use this graph to ask if I want to guarantee that for 90% of the virtual calls, I examine, I analyze the expected target, how many targets do I need to choose? So in the case of this linear graph, you can see that it's not that good because I still need to consider 90% of the targets. But what we actually get is this graph, which you can see that we can see from that using only 2 targets would actually suffice to reach coverage of 90%. So we've reduced the number of targets from 71 targets per call to 2 targets, which is pretty drastic. Another reason I'm showing you this graph is because we can use it to compare our models to other models and metrics we've considered. Specifically, edit distance metrics instead of using a model at all, which required 22 targets, and fixed order models instead of variable order models, which still required 18 targets. So obviously, as you already know, we only need 2. So these statistical language models outperform the alternatives by 9 times and 11 times for each of the alternatives. Yeah, well, I'll summarize. What we showed here is a statistical solution to a problem that would otherwise be considered extremely difficult, and it's extremely hard to give it a non-statistical solution. And this solution can, as you saw, can drastically reduce the number of targets per virtual call. And as a matter of fact, across all of our benchmarks, we found that for 80% of the virtual calls, we managed to rank the expected target at most 3, which is a very good result, especially considering that some of the benchmarks had more than 71 types. And the strength of this approach, the power of it, lies in the combination between program analysis and machine learning, in a way that using only one of them, doesn't matter which one, wouldn't suffice to get us the same level of results as we saw here today. So thank you for listening. And any questions?
Hi, Paul Bieligiti at Zurich. So it seems that you try to predict the types one by one. Have you considered using structured prediction, as it seems to fit very well this setting, where you predict all the types at the same time and try to optimize the overall likelihood?
Yeah, we're actually thinking about it right now. Other models, such as conditional random fields and others, which allow for joint predictions, might prove very useful in this scenario. We didn't get to it in this work, and we're planning to try it out in the next few months. So. But I'm pretty sure it's going to be useful. The joint predictions will probably improve the results.
And can you maybe say me more about the accuracy of the static analysis? So how many traces I need to be able to annotate manually to constitute my training data to predict the rest? Is it 10%, 20%?
Well, that's a good question. And the problem is that it varies between benchmarks. If you have a benchmark where all of the types are very similar to each other, you're gonna want more tracelets. If the types are relatively different, then fewer tracelets can be enough. In this work, we just took all the tracelets that we can get from the binary and use that. I think that's the way you will probably do it in a real-world scenario. But the ratio between labeled and unlabeled objects varies from benchmark to benchmark.
Thank you.
Well.
Hi, I'm Fan Long from MIT. I just have a question regarding about how sensitive your static inference to the trace coverage. So you're relying on traces to predict the types, right?
No, how sensitive to what?
To the trace coverage. So you rely on traces to predict types. So have you done an experiment to exclude some of traces or use only partial traces you collected? And then what's the experiment? What's the accuracy you will get?
Well, yes and no. We've tried to exclude some of the actions to see how they affect the results. And the three kinds of actions that I showed you here, the field accesses and the calls, these are the major ones that you need the most. But we haven't tried to throw away part of the traces that we had altogether. Like I said before, we try to use all the data we can get from the binary to simulate a real use as much as possible.
Okay, thank you.
Okay, thank you.